everybody. It's time to hear Professor Spinellis' wonderful talk, Software Engineering in the Cloud. Big warm round of applause. Thank you.
Good afternoon. Thank you very much to the organizers for this wonderful opportunity to be with the community. Let me introduce yourself. As you've probably gathered, I enjoy writing technical books. I also teach and head the Department of Management Science and Technology at the Athens University of Economics and Business. I try to keep myself current by writing code. For 4 years, I was editor-in-chief of IEEE Software, the magazine that tries to bring together software theory with practice. I advise you, if you don't know it, to look at what type of articles it publishes. And as I said, also in my copious free time, I try to write code such as the C-Scout refactoring browser. If you write C code that's showing age, you can use it to freshen it up. UML graph to create diagrams from UML diagrams from textual specifications. A shell for Unix that allows you to create nonlinear pipelines. Git issue management through the command line, and also a repository that combines the Unix history from 1969 until 2019, all in one Git repository. So, what are we going to talk about today? Let me tell you a story. In 1972, David Parnas, a famous software engineering researcher, published a paper in the Communications of the ACM on the criteria of decomposing systems into modules, so something that we do as programmers every day, how we break a big system into smaller modules. And in it, he described a problem that is of creating a keyword in context index. So imagine an index of all phrases showing each keyword alphabetically. And what he wrote at that time is that under extreme circumstances, a huge database, no supporting software, a system could be produced by a programmer in a week or two. How long do you think it would take you to do that? Order words alphabetically. Okay, this is how you solve the problem in 1990. It's a Perl one-liner that does this, so obviously it's not a week or two, it's perhaps a few minutes, and you now realize why some people call Perl a write-only language. What does it take to solve the problem nowadays in 2019? Well, it's again different. The data we are going to use and apply may be huge. The users that we might have to satisfy are billions, and hardware advances have not kept pace with the data increases. So we have many more users, huge data sets. Think about indexing the web, for example, something that Google or Microsoft are doing, and hardware that's not going as fast. So here is Moore's law, and you see that the number of transistors is doubling every 18 months. This has been happening from 1970 until 2016. But if we look at CPU clock speeds, you see at the end that this is not advancing at the same rate. So hardware speeds are stalling. So the scale of the problem and this stuttering of CPU clock speeds is changing the nature of software engineering, what it takes to develop software. From developing computer software, we are moving into developing systems at the scale of data centers. We are no longer building small monolithic applications. We heard that many times in the morning, but we are working in a different way. And this has a parallel. Early computers, such as the 1940s ENIAC, used to be programmed through plugboards. So if you wanted to solve a different problem, you used to take cables and connect them in a different manner. And through connecting these racks, one of those racks might be an accumulator, something that adds, you could solve a different problem. Nowadays, we program our processing with high-level languages, which are a lot more flexible. Similarly, traditional data centers are located perhaps at the basement of a company or a co-location facility, are often hardwired to perform a specific task. So here is a very extreme example. The bottom boxes are web servers, and the one on the top is storage appliance. Contrast this with cloud-based data centers, what we are discussing throughout these days, which provides us general-purpose blocks, exactly as we saw with a general-purpose programming language, not plugboards, not specialized appliances, but general-purpose. So servers that allow us to use them in any way we want. In addition, anyone armed with just a credit card can create a complex and very sophisticated data center. You just go to a cloud provider and you pay, and you can obtain computers and servers and services and so on. And this means we need to software engineer these things. Obviously, we can't learn how to do this in 30 minutes, but I will try to give you an idea of what is involved and an indication of what tools we should be using for this purpose. How many of you are using Rundeck? Don't see many hands. Puppet, Ansible, or Chef? Okay, that's good. Nagios, NetData, Ganglia? A few hands, okay. AWS, Azure, Google Cloud Platform? Great, so there's something for everyone, and we'll see interesting uses in the coming minutes. I'm going to base the presentation on the areas of software engineering, and I'm going to do that through an authoritative reference, the software engineering body of knowledge, something the IEEE Computer Society has created to discuss all elements that the software engineer should know. These are the elements that are in this software engineering body of knowledge. I will cover the ones in bold, so design, I will talk about cloud components, AWS, Azure. Software testing, I will mention Nagios and NetData. And software engineering process, and I will describe Rundeck. So let me start first with design, how we're going to design the systems. Again, let's look at the parallels between software design and cloud design. Existing software design strategies, there are many. Here are some examples. When we move to the cloud, we may need to make similar decisions, similar types of decisions, what we are going to build or what we are going to use. Some are saying that if you don't reuse at least 70% of code in your application, you're doing something wrong. How we choose the abstraction level, are we going to use infrastructure or a platform or a specific software as a service? What types of components we're going to use? And how our requirements are mapped to components. Consider AWS, which offers hundreds of services. As an example, you may need to store some data in a relational database. You have a choice. You could either use by a computing facility, EC2, and install your own database server there, or you can use that as a service by using Amazon's RDS service and use that directly. There are advantages and disadvantages in both decisions. And the services cover more than 30 application areas. For example, these include computing, how you're going to compute and process your elements, databases, storage, and many others. Similar facilities are provided by all major cloud providers, perhaps at different scales. So Microsoft Azure offers a similar variety of services. What other issues do we need to look at when we are designing? How we will handle concurrency. We mentioned that we have many more users, so we might think of how we're going to divide the data, perhaps through sharding. Some of our users are served by one data center or by one server, and others by another. How we're going to keep our service reliable. If a server falls down, what will happen? We might use replication. How we're going to handle event handling. Are we going to outsource it to our cloud provider, or are we going to handle it on ourselves? How are we going to persist our data? What we're going to do with distribution on a planet scale. Maybe we don't want a specific data center in one area to be our single source of failure. We might want to have multiple data centers around the Earth cooperating between them to give us higher level of reliability. But on the other hand, there are regulatory issues. You might not want to move personal data outside the European Union, for example. There come issues of confidentiality and integrity. Who do we trust? How do we trust? And how much do we trust our cloud provider? Who is providing identities? How do we handle two-factor authentication? And also various cloud design patterns. Let's now continue from design. I outlined the issues into construction, where I will also discuss tools. An important issue here is system configuration management. So others have mentioned it already. We view our system not as the ENIAC we saw before, plug boards that we connect with static cables, but as software that we can configure on the fly. We configure it through code that we write, and this changes how our data center is managed. So we have our system managed as software. This allows us to anticipate change. We heard before how we can abstract the configuration of our operations, And this makes it a lot easier for us to move from one vendor to the other. We're using perhaps Amazon, we decide we don't like their pricing for the specific needs that we have, and we want to move to Microsoft. If we abstract how our systems are configured, and it is specified, say, in Ansible or in Puppet, this allows us to move this configuration to another provider. If we are too tightly bound to the specific services a specific vendor provides, say Microsoft or Google, then it makes it more difficult to move to another one, say Amazon. This allows us also to reuse elements. So we have many projects running in parallel. We have coded one, how our systems are configured in one. We can take this directly and apply it in another one. For instance, I'm managing many servers using Puppet. I have some specific configuration that makes the environment easier to use and more pleasant for me. Some tools I absolutely need to have, some editor configurations, some keys, and this module I reuse across any server I manage, be that at the university or for private use. Then it has to do with management, how we plan, how we measure our performance, and we can also invest on the quality, so we can look at how well commits are documented. Somebody else can review them. We can have history of faults that are associated with specific modules and see what problems we have there. So the idea here is, and something if you're going to go away from here with one idea, is don't configure systems by hand. Never create a configuration of your system by typing in commands at the command line, or even worse, at the graphical user interface where there's no recording absolutely. Modern cloud computing systems are very complex. You have tens or tens of thousands of hosts, many services that have to work together, many components that have to cooperate, and the breakage in one of them can bring down your entire service. What you need here is automated configuration. So the golden standard is to be able to configure all your servers through a single command. If you have a blank server and you press one command, the server should end up in the way that you require it. So what we want to automate, hosts, specific hosts, what they will have, available users and roles that we have an administrator with these capabilities, an operator that is allowed to do these things, what software you have running on a specific host, a database or some management software, what services should be running, say a mail server or a web server, configuration files, how are these configured, who is allowed to access what things, tasks that are scheduled at 3 o'clock at night. You need to run your backups, for example, or you need to perform some batch processing at the end of each month. None of these things should depend on manual operations. They should be automated so that you can review them and work with them throughout the day. The same goes with networking, with storage, with monitoring, with security. What are the benefits of doing this? Don't kid yourselves, this is not for free, so it's a lot easier to type apt-get install something on a Linux box than configuring Ansible or Puppet to do it. But once you master the learning curve, it's doable. It's perhaps 50% more work, but there are many benefits. First of all, it's very easy to deploy a new host. You just run the specific command, the host is configured. As I said earlier, it's very easy to move to a different environment. You take your configuration files and you move them to a different provider. You put your configuration files under revision control, so under Git, for example. You treat them exactly as software, and this allows you to see what changes have been done, who did that change. You know Git blame? Okay, you run it and you see, yes, of course. You see, who did that silly change? Okay, let's go and ask him why, what was he thinking at the time, what was he smoking, perhaps. You can track issues and associate commits with specific issues. You can repair a misconfigured system. If it doesn't behave well, you have two options. You can shut it down and start a new one from scratch, very easy, or you can run again Puppet, and Puppet or Chef will reconfigure it in the way it should be. And you also have executable documentation. So your configuration is your documentation. You can read it and see how your system should be configured. I configure systems with tens of modules. Others configure systems with hundreds of modules. There's no way an administrator could have in their mind how the system should be configured. But if you have that under configuration management, you can easily search there and see what should be done. Some notable tools in this area are Puppet, Terraform, we heard earlier, Chef, Soltac, Ansible, CF Engine. Let me give you some examples through Puppet. It covers things like the infrastructure, appliances, services, scheduled tasks. The rules have preconditions, what should happen before something is executed, and post-conditions, what happens after a rule is executed. So here's an example. If I want to have postfix installed, postfix, not postfix, and I say ensure present, that I want always this package to be present. I can do the same with files and services. So here's a file example. I'm writing here that the file, etc. postfix main CF should be owned by user and group root. In order to be installed, we need to have the package postfix installed, so this is the precondition I mentioned, and the contents of this specific configuration file are located in this file that I manage. And this is a service example, so I want the postfix service to be running. I want to have a mail server, and for it to be running, I need to have this package and this file, and this should always be running and enabled. So by specifying this, I specify declaratively, not through commands, that my system should behave in this way, should satisfy these conditions. If something isn't working like that, it will be made to work like that. If the service is not running, it will be brought up. If the file's contents don't match what I have said, they will be made to match. We can build up from there, looking at modules, at nodes, at inheritance, so some system can inherit properties from other. These goodies I mentioned at the beginning are inherited by all systems I manage, and also client-server configuration. So you have one server managing tens or tens of thousands of clients. In addition, there are many modules that you can find ready, and you can use them directly without writing your own complex configuration. So some modules that you can find include things like firewalls, servers, languages, AWS usage. Here is an example of using a module where I'm configuring a virtual server under Apache with these rules. So this is not something that's built into Puppet. It's a module that provides you this functionality to specify how you are handling WSGI or how many threads the server should use. Let's move to the next element. What's going on here? It's a NASA air safety experiment. They are crashing a plane with a new type of fuel to see what happens if it will explode or not. We are not doing so dangerous things, but still we should be testing our systems. And this, in the area of software, there are specific techniques. In cloud-based systems, the rules here are a lot of continuous monitoring at various levels. So at the level of your infrastructure, how's your cloud provider operating, at the level of your middleware, your services, and at the level of specific software applications you may be running. We'll give you an example of a tool here, Nagios, which can be used to monitor your infrastructure. There are also other tools, but I will try to explain what needs to be done, and any tool that satisfies this is obviously fitting your needs. So what can we do with Nagios? We configure specific servers, and we can see their health. So here is an overview of a number of servers. It tells us that the servers are up, and the number of services that each server has is 12 or 10 or 24, and they are okay, green, which is nice. At a more detailed level, here there are specific services per host, and you see that some services have a warning. So some pings are not, a server is not responding to pings, GitHub in this case, because GitHub as a provider of a service is part of something that I monitor, or the number of users on this server is critical, it is red. You can also obtain statistical details to see things that are flaky, and maybe we need to do something, invest in a better provider, or somehow offer more redundancy for a specific server, both as numbers and in a graphical form. How do we do those wonderful things? We specify objects, so services that we are running, commands that we can run in order to get notifications. I sleep too much at night, so it would be a good idea to get woken up with an SMS when a service goes down. I can specify this with a specific command. Things we can do to check specific hosts, and also things we need to check specific services. So all these are configurable. If you create a new service for your organization, say a gadget that allows you to run with a robot and run tests, if a test fails, you need to get notified. you can create a command that will send you such a notification. You can also specify host groups, so if you have 100 similar servers, you can have them all specified under a single group, so all will be monitored in the same way, and also templates that allow you to parameterize various things. So here's an example of a server specification. I'm using a template. I'm specifying the name of the server, an alias for it, who should be contacted, who are the poor souls who get an SMS if something goes wrong, an image so I can see it graphically, and a status map to show where it is, where it appears in this image. This is an example of a service specification. It applies to a specific host group. Here's an example of a service specification. I'm checking whether there are some updates provided by Amazon. Again, I don't want to be running a stale software. If Amazon provides some updates, I want to be notified. So I'm creating a service that will turn to orange or red if there are updates and these have not been installed. You know that many important security incidents have been were the fault of administrators not installing security updates. The Equifax case was a specific large example of this. Here are some commands I'm defining in order to check various things. So whether the load is too high, whether the disk space is running low, or whether we have HTTP connectivity or not. There is also a remote plugin executor that allows us to execute plugins at remote hosts. As you can probably guess, there are also, of course, many plugins, more than 5,000 plugins that are already available. You can download them, other people have written them, and you can use them to monitor various services, so you don't need to reinvent the wheel. Here's a list of various plugins. Nagios gives us a picture of the systems that we monitor, but it doesn't allow us to see easily trends regarding performance. For this, a very nifty tool is NetData. How many of you are using it? It's one of the most popular monitoring tools on GitHub. It's developed here in Greece by a person who was really fanatical about monitoring their system. Is this an example of the picture it gives you? You see trends, you see how your hosts are operating, the load, and all this in real time with very little load on the servers that you are monitoring. Let's now move to the last part of the software engineering cloud applications, the software engineering process. So how we can best implement processes that have to do with operating our systems. What do we need to do here? Perhaps handle our crowd resources, fire a few more servers, bring some servers down, install a new update of our software, give specific roles to our personnel, automate some operation processes. What do we need to do here? We need to manage them through workflow automation. So, as you probably guess, I enjoy typing things on the command line, but this is not the best way to engage with our operations people. Mistakes can happen. Some consider the command line unfriendly. Somebody asked earlier, how do you exit VI? Okay, we don't want these questions to happen in a critical situation. We want things to be more automated and easier, more accessible. One way to do this is a tool called Rundeck, whose purpose is workflow automation tool. So you have various workflows in your organization. Perhaps, as I said, bring up a new server or install a new version of your software. You want to automate it, and you can have procedures that you script, and these become self-service jobs. So you have people who are operating your servers 24/7. You can have specific procedures that they can run with a touch of a button. This gives you easy control because, again, you manage this as software. I put Rundeck scripts under revision control management, so I run them under Git. And visibility, you have a log file, and you can see who ran what and why. What you do under Rundeck, you define projects. Under projects, you define jobs. You may have tens of jobs, so you can group them into groups. You then specify nodes. These are your servers, commands that you run on them, and you can also monitor the activity on those servers. So who went and installed a new table in the database or deleted a record. Here is an example of some jobs grouped into categories. You can create jobs interactively, so through a graphical interface by specifying their parameters, how they are run, and what happens whether they succeed or fail. So maybe when you bring up a new service and it fails, you very quickly need to bring it down and bring up the old version that actually works correctly. Then, when operations execute a job, they can specify its parameters. So we are under a heavy load. We need to bring up 100 new servers. Here's a screen that fires up 150 nodes, computing cluster on AWS. So at one point, we needed 150 more computing nodes. We had a screen, we could specify 150, press run job now. A lot of money flows out from the credit card. 150 hosts are up and ready to compute in a few minutes. As you can imagine by now, Rundeck also supports plugins. Every self-respecting service or software supports plugins nowadays, and this can allow you to automate various things, again, ready from the box without having you to write them from scratch. Let me summarize the 4 types of cloud software engineering tools that we saw together in processes. So at the level of systems and design, we want to use the tools of our infrastructure, so AWS, Azure, or Google's computing elements. For system configuration management, we can use Puppet or CF Engine or Ansible or Terraform for system configuration management. We want to monitor our operations with Nagios or NetData or Ganglia. And finally, we want to automate the operations of our workflow through a tool such as Rundeck. Thank you very much.
All right, I think we have time for some questions. Shall we switch over to the questions screen? And I think
Zero questions, thank you. Bye.
No, don't go. Wait
okay,
a second. Huh? Guys, do I see any hands raised? Or
See a hand here.
There's one here. Good.
Sorry.
Innocent.
Okay, no, not really. So, recently Amazon, I was involved in a sort of upheaval in the open source community where it took MongoDB, the open source project, which many projects use. They hardened it, and they called it DocumentDB, and they started charging for it. Do you foresee some kind of a change of attitude? And actually, as a response to that, a lot of open source projects started changing their licensing terms. Do you foresee that we need some, I'll call it a more automated way that on the tooling side to actually check for licenses for all the, possibly tens of components that we're actually using in building systems? That's the question.
So the question is whether we need better compliance monitoring tools for the open source tools that we are
just
using.
like for security and for other.
First of all, let me remark that what Amazon did was not necessarily against the license. GPL allows you to use their service, a product to an open source project to create a service. If you want to avoid that, if you want to say that I don't want Amazon or Google to use my open source project, then there is a more restricted license, the Affero GPL license, that says that you cannot do that without open sourcing what you have done, so that hardening that Amazon did would have to be open as well, which I assume you are mentioning that it's not. The other question, part of your question, I understand, is how we can monitor compliance. I know that large companies are creating programs to do that automatically. There are tools that do it, and there are mechanisms that make it easier for you. So one example is the SpeedX extension that allows every file to specify under what license it is created. So monitoring whether you have some GNU licensed parts in a system that you want to release without giving out the source code is a manner of grepping through the source code for SpeedX identifiers that contain the GNU license identifier.
Professor Spinellis, what is the best skill a software engineer should have these days, in your opinion?
What is the best skill a software engineer should have? A desire to learn, because technology is always changing, so we should always be reading, and the capability of introspection, always monitor ourselves. What am I doing here? Am I doing it correctly? Can I do it in a better way? Can I reduce the toil? Am I doing something that can be automated? Can I write a tool to do this better? Is there perhaps a tool to do this better. So a desire to learn both from others and through what we are doing, from our everyday experiences, is what makes us every day better developers. I continue to code day in, day out. I continue to learn. The Effective Debugging book is dedicated to my mentors, past and future, because we all need mentors. We need to always be learning from others. A great way to learn is by contributing to open source projects. Many are managed in a very professional way, and you can learn many good practices from that. So learning is the key knowledge for software engineers.
I think one word describes all of that last sentence. It's open. So thank you very, very much for this fantastic talk. Thank you very much.
Thank you.
And thank you very much for the books.